I would like to prove the following statement in blue by contradiction. It says if the sum of two primes is prime, then one of the primes must be 2. And before we begin, I want to remind you the definition of prime because we're going to use this and I'm going to make an observation that I haven't explicitly written down that we'll need in the proof. So the definition, as we recall, P is prime, an integer, provided it's bigger than 1 and the only divisors of P are 1 and P. And in particular, 2 is a prime number, but one thing that follows from this definition is that 2 is the only even prime number. Okay, so one thing that follows from this, okay, so from the definition, we get the following that say you have an even number. And bigger than 2. Then x is not prime. And we can see this, so I'll do a little mini proof. We can see this, for example, so from the definition of even, we know there exists some b integer with x is 2b. And in particular, this equation, x is 2b, says that 2 divides x, since b is an integer, which I just stated in the right here. And with x strictly bigger than 2, you see we have found a divisor that is not 1 and not x, namely 2. So therefore, just from the definition of prime, we have this 1 less than 2 less than x, and 2 divides x, okay? So this we're going to use, okay, so by contradiction, we must always start our proof by saying what technique we're using. If we're using contradiction, you say by contradiction, or by contrapositive, something like this. Okay, so we will assume, well, this is saying something about the sum of two primes, so we're going to need two primes. So assume P and Q are primes with the sum of two primes prime. This is the statement A, okay? So far so good. Now we have more to assume. We assume that negation, or the opposite, we assume that B is false. So, and one of the primes must be 2. If you negate this is really there exists. The negation is not the statement, one of the primes must not be 2. It's that neither prime, neither P nor Q is 2, okay? So this, everything I have written is what we're assuming in our proof by contradiction. So now let's begin. Well, if neither of these are 2, then they both must be odd. We just discussed this. So then, P and Q are both odd. Okay, because 2, the only prime number, we just discussed that. So then we have there exists, so period, there exists maybe A, B integers with P is 2A plus 1 and Q is 2B plus 1. And now we just add because we know something about this, P plus Q. So let's add that and see what we get. Okay, very good. So then P plus Q is 2A plus 1 plus 2B plus 1, which is 2A plus 2B plus 2. But look here, this is 2A plus B plus 1. So this sum is even, as A plus B plus 1 is an integer. Okay, this is where we'll see we have a problem. Okay, because we have to look at P plus Q. Our assumption is that P plus Q is prime. Then we work with our other assumptions to show that P plus Q is even. If you take what we discussed that followed from the definition of prime, we can conclude, so then P plus Q must equal 2, okay? Well, here's where we're going to get a contradiction. Because let's look at our assumptions, right? So these two are both prime, P and Q, neither one is 2. So P must be strictly bigger than 2. Q must be strictly bigger than 2, excuse me. And then P plus Q must be strictly bigger than 2 plus 2, which is 4. This is definitely a contradiction because it says that 2 must be strictly greater than 4. We have a contradiction. Because 2 is not bigger than 4, okay? And you can, that's the end of the proof. So therefore, the original statement here in blue must be true. We assume the opposite. It led to basically saying 2 is bigger than 4. And therefore, that's the proof by contradiction. Very good. Here's another example that will use contradiction. So we take a real number bigger than 1. And we want to prove the square root of A is between 1 and A, strictly between. Now, I'm going to rephrase this in terms of sets. So we want to show the following. If A is bigger than 1, then the square root of A is in this open interval 1 to A. That's exactly what this statement is reading, an if-then statement. And to do this by contradiction, here's our if and our then. So by contradiction, we want to assume this and that the square root of A is not in this open interval. Okay, well, you see there's really two things we might know. Either the square root of A is less than or equal to 1 or is bigger than or equal to A. Okay, so we need to treat those two separately and get a contradiction. So this means, I'll write that, this means the square root of A is less than or equal to 1, or the square root of A is bigger than or equal to A. Okay, so let's work with this assumption, and we will get a contradiction. Then we will work with this one, and we will get a contradiction. Okay, so if the square root of A is less than or equal to 1, I can multiply both sides of A less than or equal to with a positive number, and it does not change the less than or equal to. So we have, if I just multiply, we will have that 1 times square root of A, and this says that A is less than or equal to square root of A. Okay, now, then squaring both sides, we obtain that a squared is less than or equal to a, okay? For positive numbers, y is x squared is an increasing function, and so we can keep this less than or equal. Well, at this point, we can just divide. So since a is not equal to 0, we can divide by a. And we get a is less than or equal to 1, which is a contradiction. Because our assumption was that a is bigger than 1. So we contradicted one of the assumptions. Okay, that's fine. We have a contradiction. Now let's think about this. So if the square root of a is bigger than or equal to a, well, we're going to have almost the exact same argument, as you will see. Let's just square both sides. And we get that a is greater than or equal to a squared. And again, we divide by a. One is greater than or equal to a, which is a contradiction. Therefore, the square root of a is strictly between 1 and a. If you wanted to, especially in this case where we had it looks like two different contradictions, even though the logic was very similar, you can make a little statement at the end like that. I want to do another proof by contradiction because this is a super famous proof that you should see in a beginning proof course. It's that the square root of 2 is not rational. And the nice thing about this, or maybe the different thing about this than the other two we have done, is that here, this is not an if-then statement. It's just a statement. Square root of 2 is irrational. And we know in a proof by contradiction, you just assume the opposite. And, it doesn't have to be of the form if-then. And then you work until you find something that's always false. So in this case, we will begin by contradiction. Okay, well, we assume the square root of 2 is an element of Q. Now, every real number is either rational or irrational, and if you're not irrational, then you are rational. And Q is our symbol for rational numbers, as we have discussed. Okay, very good. Well, we need to unravel what this means. Okay, so then we may find two integers, say x, y, integers with no common divisor bigger than 1. And the square root of 2 is equal to x over y. Sometimes you will see this as, writing the square root of 2 in lowest terms. So for instance, we would not have 2 over 4 in lowest terms, it would be 1/2. We would not have 7 over 21 in lowest terms, that would be 1/3, etc. That's what I mean by this. Maybe I'll even add that in parentheses. What I mean by this is that this is in lowest terms, but the meaning of lowest terms is exactly what's above here. They have no common divisor. You can't divide out anything from the numerator and denominator to make it a simpler looking fraction. Okay, so now let's just multiply through. So then we have the following. We have that x is the square root of 2 times y, And if we square both sides, we get that x squared is equal to 2 times y squared. So this shows x squared is even, because y squared is an integer. Okay? Well, I'll put a claim that I will use, and that's for, maybe call it A. If A squared is even, then A is even. Okay, this is true. And the cool thing is that we've actually proved it. So let's take the moment to see why we've already proved this, and you may not know it. So what is the contrapositive? The contrapositive, right? We know the contrapositive of an if-then is logically equivalent to the implication. We would negate this, and then we negate this. And I hope you remember we did this, right? This was our very first proof, okay? So we proved this in class. And so in particular, the claim is true. Okay, very good. So now let's return to our proof. Maybe I'll put a red line, because I had to, many times in the middle of a proof, you might come to the side, do a claim, and then maybe you need to prove it. We didn't need to because we already have, but I need to make the comment as to why it's true. Okay. So this shows x squared is even. So therefore, using the claim, x is even. Okay, so then this means there exists. I need another letter. I don't want to use A, maybe a B with x equals 2b. Okay, now let's just go back to this equation. So I'm returning to this right here. Okay, and I'm going to put in 2b. So I have 2b squared equals 2y squared, or 4b squared is 2y squared. We may divide by 2. 2b squared, y squared. Okay? Guess what? This looks like something we've seen. It looks like this one, except we have the y over here. So this shows y squared is even. As b squared is an integer, and hence y is even. Again, using our claim. Now, put my markers down. This is the moment you should be able to think about what is the contradiction, because we have everything here. So what we have is we have two numbers, x and y, and let me underline some things we've shown. X is even, y is even. Okay, let me get my eraser. 2 is a common divisor. To x and y. And this is our contradiction. We found our contradiction, okay? We had a common factor of both x and y. They're both even by this argument. And therefore, we can conclude the square root of 2 is not an element of Q, or in particular, it is irrational.